Oh my god. Oh dear. Are you filming?
Yes, I'm filming.
In a couple billion years, our sun will become so violently hot that it could wipe out all life in the Milky Way. But as it gets stronger, it could also help us live on places like Pluto and Saturn's moons. How can the center of our solar system be so giving yet destructive at the same time? Well, in today's episode, we're going to go through the entire evolution of the sun, from how it helped create life on Earth to how it could one day destroy us, one day old. 4.6 billion years ago, the first outlines of our solar system started to emerge. Seeds of new life sprung up from the remnants of older stars which had exploded. A huge cloud of dust, gas, and vapor emerged. This gaseous cloud began to collapse under the force of gravity and started to rotate. Then a dense core formed at the center. Meanwhile, the rest of the cloud had flattened into a disk that rotated around the central core. Smaller bits of dust and gas gathered together and began to form the start of our planets. The dense core began to heat up, glow, and exert pressure. This marked the birth of a protoar, kind of like the baby version of our sun. This was a ball made up mostly of hydrogen and helium. If you'd been around to see it, the protoar would have looked quite dark. Within the first 10 million years, the gas giants Jupiter, Saturn, Uranus, and Neptune were formed. Inside the protoar, the temperature and pressure kept growing. Finally, after 50 million years, something massive happened. The baby protoar reached pressures and temperatures high enough for nuclear fusion. Hydrogen atoms fused together to form helium. This gave off huge amounts of energy, and our sun was born. Then, over tens of millions of years, the rocky planets Mercury, Venus, Earth, and Mars were formed. Began its childhood. It was now burning 603 billion kilowatt of gas every second. The energy given off in just this 1 second would power every household on Earth for the next 800,000 years. It's also incredibly hot. The surface temperature is 5,500 degrees C, and the core could be as hot as 15 million degrees C. The sun started off with enough hydrogen to keep it going for about 10 billion years, which makes it the single largest object in our solar system. 1.3 million Earths could fit inside here. If the sun had been smaller, then Earth would be in big trouble, like if it had become a brown dwarf star. This is a much smaller star that can never reach a core temperature high enough to ignite. Lucky for us, the sun was big enough to start powering nuclear fusion inside. This allowed it to radiate heat and energy, which helped Earth create and sustain life. Okay, we all know that the sun is incredibly hot. But let's dive a little bit deeper into what is happening with this massive star. In the sun's core, nuclear fusion reactions are going off constantly, the equivalent of 15 billion atom bombs every single second. So why doesn't the sun explode? Well, for every second of its existence, the sun is involved in a balancing act known as hydrostatic equilibrium. There are two forces at play here, each of which counter one another. Think of it as a tug-of war between two equally matched teams. If each team pulls equally hard on the rope, it stays in one place. That's kind of what's going on in the sun. The strong gravitational force inside the core pulls inward, and this is offset by the massive energy from the nuclear fusion reactions which push outward. These two forces balance each other out. Okay, at this point, our solar system has now completed its first full orbit around the center of the galaxy, or what we call one sun year, which lasts 230 million Earth years. Happy birthday to the sun. Sorry, I forgot to bring a cake, but it had likely burn up or melt. Anyway, this young sun is only 70% as bright as our sun today. Think of this stage as the sun going through its emo teenage phase. No riz for the next 4.5 billion years or so. Things continue at this steady pace. Because the sun is in a state of hydrostatic equilibrium, the nuclear fusion reactions continue without major changes. You might almost think this stage is kind of boring, but you'd be wrong, because there is one change which occurs very gradually, but it will be a big deal for all of us here on Earth in the future. It's the brightness. As the sun ages, it gets brighter. Why the pressure increases? The increased pressure causes the sun to run at a higher temperature, increasing its brightness by about 1% every 100 million years. Now, 1% brighter every 100 million years might not seem like much, but over time it adds up. Remember, it's been up there for a few billion years. The other thing that's adding up is helium inside the core. Remember this, as it will be incredibly important later in the sun's journey, 4.6 billion years old. Okay, we're now in the modern day. The sun has reached middle age. Today's sun is 30% brighter than the young sun, and its nuclear fusion reactions are going strong. Now, with millions of these fusion reactions happening every second, will the sun never stop? Well, the sun only has so much hydrogen left. So the answer is, of course, yes. But luckily, we have about 5 billion years left to go. So most of you won't see the sun die out in our lifetime. Now, if the sun was 10 times bigger, it would burn all its hydrogen much faster and die out sooner. A sun this size would have only burned for about 20 million years. And that's before any life was created on Earth. And if our sun was half the size, well, it would have been a red dwarf. And this type of star lasts anywhere from 80 to 100 billion years, but it's much more dim and significantly cooler than our star. So let's just enjoy the 10 billion years we have with our sun. Alright, now that we've seen what's happening with the sun in the modern day, let's jump ahead to the future, 5.2 billion years old. Fast forward 600 million years into the future. The sun's luminosity has increased by about 6%, and that means the amount of solar radiation hitting Earth has increased, which is bad news for any life on Earth. Increased radiation causes carbon dioxide to leave the atmosphere, and this makes it nearly impossible for photosynthesis to occur. So plants will start to die off, and the plant's gone, animal life will die out too. The only place life might be able to survive will be in the oceans. 5.6 billion years old. Okay, fast forward another 400 million years. The sun is now 10% brighter than it is today because the denser helium in the core is making the fusion run hotter. Earth will also be much warmer. It'll become a greenhouse similar to Venus. Our oceans will evaporate. And as this is happening, the atmosphere will be saturated with water. This then splits into hydrogen and oxygen due to the heat from the sun, and the gases will escape, and the carbon cycle will come to an end. What was once a planet bustling with various ecosystems is now a lifeless rock. So, what once gave us life is now the thing that's killing us. Let's just hope that humans have learned to live on other planets by this point, maybe even other galaxies. Okay, 4.8 billion years in the future, the sun is now an angry old man trying to send back soup in a deli. It's 67% brighter than it is today. But just as angry old men do, it's slowly winding down. The hydrogen fuel in the core will slowly be running out as it transitions to its next phase. The layers outside the core will expand and cool, so the sun will become brighter and larger, but it'll still be relatively stable. If you stood on Earth and looked at the sun, it would be a bright red sphere, and appear to be 1.5 times the size of the moon. But sorry, bad news. Even if you were around, you wouldn't survive. Earth at 300 degrees C will be like a pizza oven, a hard, dry rock, devoid of any water or any life, and it would be pretty much impossible to look at the sun. As the sun hits old age, it'll become a red giant. The hydrogen in its core is exhausted, and helium has piled up. The sun's helium core has reached a mass of 140 Jupiters, and now it's at a breaking point. Core pressures and temperatures are incredibly high. This heat reaches the sun's shell, and hydrogen in the shell surrounding the core begins to burn. 500 million years later, the sun will be 34 times as luminous as it is today. And Earth will be hot. If you were to sail a ship on Earth's surface, you'd be riding waves of molten aluminum and copper. In another 85 million years, the sun will be 2,300 times as bright. Even your darkest sunglasses couldn't save your eyes. The enormous energy given off by the sun will cause its outer layers to expand. Earth will be reduced to its iron core, or it could be vaporized altogether. Now, the increased radiation from the sun might erode the atmospheres of Jupiter and Saturn, but there's a possibility Jupiter manages to survive. And there's another place that might suddenly become habitable. That's Saturn's moon, Titan. With all the radiation from the sun melting its ice, it'll have liquid oceans of water ammonia and might even feel like Earth. And Pluto, still not a planet, could turn into a tropical paradise. At this point, the sun is burning more nuclear fuel every 6 million years than it did during its entire 12 billion year lifespan. A phenomenon that's clearly unsustainable. Helium keeps piling up in the sun's core. The core now contracts, becomes super dense, pressurized, and hot. It's reached 100 million degrees Kelvin. Then something astonishing happens. This is called, or will be called, the helium flash. This flash makes the sun's core exponentially hotter. And as this is happening, the sun will be brighter than all the stars in the Milky Way galaxy. But another weird thing is happening. The energy of the flash counters the extreme pressure inside the sun. So not much energy reaches the surface of the red giant. But everything that's going on transforms our sun. The core gets heated so intensely that it vaporizes, expands like crazy, and as a result, cools violently. In a quick 10,000 years, the red giant shrinks and dims to less than 2% of what it was. It's still 10 times the diameter of our current sun, and 40 times more luminous. But compared to what it was, it's a mere shadow of itself, a subgiant. The sun is now an orange-ish yellow subgiant star. There's a feeling of déjà vu as what happened with its hydrogen is now happening with its helium. Over the next 100 million years, the sun will burn helium at an incredibly fast rate, 100 times faster than it was burning hydrogen. As it's burning helium, the sun's core changes, becoming a carbon-oxygen core, 12.1 billion years old. Okay. Finally, all the helium in the core has burned. Now the helium in the outer shell starts burning and the sun becomes a red giant again. This time with a carbon core, but the carbon doesn't burn in a flash like helium did. Despite the high pressure in the sun's core, it's not high enough for carbon to fuse. The high temperatures in the core heat the outer layers, and they expand even further this time beyond the orbit of Jupiter. The core gets very dense and becomes a white dwarf. Soon, the core and outer layers start to come apart violently. In a series of spectacular eruptions, the outer layers of the sun will split away from the core and be flung away. Kind of like Marie Kondo decluttering the sun. Half of the outer layers will engulf the entire solar system and then disperse to become one with interstellar gas. The other half will be pulled into the dense white hot core. It would look like the sun was going from red to white. Now if these violent eruptions all happened at once, the sun would lose mass and its gravity would weaken very quickly, allowing planets to escape into space. But this is no half-hour episode of Marie Kondo. This decluttering happens over millions of years, kind of like cleaning my garage, so the remaining planets and objects from Jupiter to the Kuiper Belt stay bound to the sun, even though they're tied with a weaker gravitational force. Their orbits move further away. Now you probably remember that Mercury and Venus got swallowed up by the sun in its first red giant phase, Earth too. But what about Mars? Well, based on scientists' calculations, Mars has a good chance of surviving both the first and second red giant phases. The sun's core will be extremely hot, around 170,000 degrees Kelvin, and it'll be about 4,000 times as bright as it is today. The energy radiating from the sun will light up the gases around it, creating a spectacular planetary nebula. But in just a few thousand years, this nebula will fade and die out. Okay, at this point, the sun is now a white dwarf. It's no bigger than Earth, but it's 200,000 times more dense. It'll spend billions of years cooling off. The oldest known white dwarfs from the stars born after the Big Bang have been cooling for 12 billion years, and they're still 5,000 degrees Kelvin. And whichever planets survive will orbit the white dwarf for billions of years more. But what if our sun were to cool down someday and finally become a black dwarf? Well, maybe in a few trillion years, but that sounds like a story for another. What if,